Thanks, Xiaoliang, for organizing this meeting. Sorry, can I get rid of this? Yeah. Today I'm going to talk about novel phases of quantum circuit protected by hidden dynamical symmetry. And this work is in collaboration with Sun Wan and A. Hood. So let's start from the background. The measurement-induced phase transition has been studied quite extensively in the past 2 years. And this phase transition concerns the setup, which is given on the left. So we consider a random quantum circuit made of random unitaries interspersed by measurement in every space and time. And this projective measurement occurs at a finite measurement rate p, and we consider the system start from an initial pure state, and this measurement basically define an ensemble of quantum trajectories, which defines an ensemble of quantum trajectories describe this stochastic pure state evolution. And the measurement-induced phase transition concerns the average entanglement entropy in each individual trajectory. And this people has already shown that by extensive numerical evidence as well as some analytic arguments that there can exist a phase transition from a volume law scaling entanglement entropy to an area law scaling entanglement entropy when you tune up the measurement rate. There are two important messages in this measurement-induced phase transition. First of all is we can understand this phase transition from the perspective of information flow. So let's assume we encode some quantum information through the entanglement with the reference in the initial state, and we evolve the system using this random circuit with measurement. And this measurement-induced phase transition can be really understood as a phase transition in the quantum channel capacity, which characterizes how much information you can transmit through this quantum channel to the final state. So there are two phases. First one is the volume law phase. Actually, it's characterized by you can transmit a finite fraction of qubit to the final state. And in this phase, the scrambling unitary protect the quantum information, and the quantum information encoded in the initial state is really retained in the system. And there's another phase, which is the area law phase, when measurements overwhelm this information protection by scrambling, and the quantum information is really revealed by the measurement. Another very interesting perspective about this measurement-induced phase transition is based on a mapping to a series of classical statistical mechanical model. So in this perspective, people have taken using a replica trick to introduce this replicated version of entanglement entropy Sn, and when you take the replica limit n goes to 1, this reduces to the usual defined average entropy of subsystem A. And in this replicated quantity, actually we can map this Sn to the difference of free energy of classical spin models with different boundary conditions. I will show in a second that the quantities, that the underlying quantity can be mapped to the partition function of classical spin model. And all the essential physics can be already seen in the n=2 model. So let's take a look at the take a look at the quantity here. Take n=2, and now that this quantity involves two copies of density matrix, and we can in general write down a tensor network representation of the quantity here. And this quantity involves two copies of density matrix and both the forward and the backward evolution. So in general, there are 4 copies of random unitaries. What we can do is we can just do some rearrangement of the gates. There's nothing fancy going on here. We just put the same unitary on the top of each other. So now in the second diagram here, each box represented actually 4 boxes, either 4 unitary or 4 measurements in the circuit, and we can rearrange the circuit in the following way. And what I want to say here is we can understand this tensor network diagram as a time evolution of the doubled density matrix along the temporal direction. And what we do further is if we can perform the average over the random unitaries in the circuit, we can really map this tensor network diagram to a partition function of the classical spin model. And in this classical spin model interpretation, the two terms appears in the entanglement entropy actually correspond to partition function of different boundary condition, and we can interpret this entanglement entropy as the excess free energy of the domain wall creation. And a few important remarks about this model is, so first of all, as I already said, we can map the double dynamics in a double Hilbert space to a classical STEMMAC model. The second is there's a effective spins emerge from the averaging over unitary gaze. And the third one is actually this spin model for n=2 exhibited Z2 Ising symmetry. And this allows a ordered and disordered phase and the ordering phase transition between these two. People have already understood that the ordered phase, the ferromagnetic ordered phase, correspond to the volume law entanglement, and that's, as we just understood from the previous slide, this corresponds to a situation when information is protected from being revealed by measurement. There's on the flip side, there's a disordered phase which is characterized by the area law entanglement, and this is really the situation when information is revealed by the measurement. Okay, okay, the current understanding of measurement-induced phase transition raises a few key questions. So first of all, is we have all seen this volume law and area law entanglement phase. Is that possible to have more measurement-induced phases other than that? Okay, second question is, we have been always studied the random unitary circuit where there's no internal symmetry. So people naturally wonder, how does the internal symmetry of quantum circuit affect the symmetry, for example, of the spin model, which governs the existence of different phases? And whether the internal symmetry will lead to new phases is another question to ask. And third question is, if there exists some novel phases from the interplay of internal symmetry and the swap symmetry, and what is the meaning of these novel phases from the perspective of information flow? Is there any sharp signature to detect it or not? Okay, so here comes the outline of today's talk. So today I'm going to talk about, so first of all, talk about the effective Hamiltonian for the dynamics of quantum information. So in this first part, I'm going to build a connection between the dynamics of quantum information in quantum circuit with measurement to the ground state problem in of the effective Hamiltonian. And the discussion will remain in 1D. And this is very important because this allows you to use some knowledge from the textbook to solve some unknown problem in quantum dynamics. And in the second part, I'm going to talk about what governs the symmetry of this effective Hamiltonian. And you will see it's in general higher than the internal symmetry of the circuit. This will allow the many novel measurement-induced phases, including the symmetry breaking phases and topological phases. In the third part, I'm going to show that the different possible phases correspond to distinct information dynamics. In the last part, I'm going to show consider a slightly different situation when I restrict the circuit to be a Gaussian fermionic circuit, and you will see the restricted quantum information scrambling will lead to, due to Gaussianity, will lead to a even larger symmetry, which is a continuous symmetry, U1 symmetry when there is a measurement, and even higher symmetry, SU2 symmetry when there's no measurement. And there actually exists a measurement-induced cos-solids phase transition. Okay, any questions so far? Okay, let's move on. So first I'm going to talk about what is the quantum circuit model I'm going to discuss today. So the circuit model is now given on the left. It contains 3 ingredients. So first ingredient is there's this gray box, which is the single qubit Z unitary, is arranged in this layer structure. And between this this gray layer of gray unitaries, there are going to be measurements with probability p. This measurement does not really restrict it to be single site measurement. It can be two site or multi-site, doesn't really matter. And there's going to be a large unitary gate, which is in general has a coupling constant being a Gaussian random variable. This allows our this will be necessary for our map. Being Gaussian measurement, the Gaussian random is not necessary, but you require it to have a zero mean. Okay, this is the circuit we are considering now. And why are we considering this new circuit? So first of all, as I said, the hard random circuit does not have intrinsic symmetry. By considering such a unitary circuit, we are allowed to study the role of internal symmetry of the circuit. And second is this allows us to study different type of scrambling. For example, if you restrict the gate set, actually this will significantly reduce the scrambling in the circuit, and we will see this will have a huge influence on the measurement-induced phase transition. And third is in this quantum circuit, actually every gate is really generated by a Hermitian operator, and this allows us to map to a continuous time model, which makes our mapping to ground state exact in a certain limit. Okay. So now I'm going to sketch our idea of mapping to ground state problems. So as I said, the crucial quantity we are considering in the measurement-induced phase transition involves this involves the evolution of multiple copies of density matrix. Okay, so one thing I forgot to emphasize, which is the measurement-induced phase transition is a phase transition that concerns the observable, which is nonlinear in density matrix. And now for the simplicity, the simplest nonlinear function of density matrix is the second moment of that. So from now on, I'm going to just focus on this n equals 2 replicated quantities, which concerns the dynamics in the double Hilbert space. Okay, as similar to the diagram we have already seen in the background slides, this is a representation of this depending on the boundary condition on the top, this can serve as a representation of the important quantities in the expression of entanglement entropy. And this concerns about the dynamics in this double Hilbert space of density matrix. And what is shown here is each gray box actually is four copies of unitary, involves the both the forward and backward evolution for both copy 1 and copy 2. And now what I'm going to show is if you average over the coupling, average over the coupling in this single qubit Z gate, actually you are going to reduce the dimension of your Hilbert space in the to a 6-dimensional Hilbert space. This 6-dimensional Hilbert space can be labeled by a spin one variable m and a spin 1/2 variable s. It turns out that in the models of our interest, that this spin 1/2 variable s is not important. It's not very interesting. It's actually a conserved quantity. You can get rid of it by using some trick. So in the end, we get the effective spin 1 degrees of freedom. And if you project the dynamics onto this effective Hilbert space, you will actually get an imaginary time evolution in the temporal direction. And what is nice about this is, as we all know, if you have an imaginary time evolution generated by some Hamiltonian HQ, and if you take the depths of the circuit to be sufficiently large, the quantum, if you view this double density matrix as a quantum state, and this quantum state will evolve to the ground state of HQ. And in this language, you can write down the entanglement entropy S2 as some matrix element between the ground state and some given state, which is determined by how you contracted the tensor network diagram at the top. This is a predefined state, and the entanglement entropy really reduces to the matrix element of that. And this tells us that computing entanglement entropy really reduces to solve for the ground state of HQ. And the symmetry of HQ determines the possible non-trivial ground states and determines all the possible interesting phases relevant to this information dynamics. And this relation is also very nice because we relate some unknown problem in the quantum dynamics to the ground state problem, where there are multiple of existing tools to solve it. For example, like DMRG and solvable models to really treat those problems. Okay, so now the pertinent question reduces to what governs the symmetry of HQ, because that determines all the interesting phases we can obtain, especially when the circuit exhibits an internal symmetry. Okay, if the circuit does not have symmetry, this reduces to the Hall-random situation. We know that HQ has this. For example, for the double density matrix has this symmetry, Ising symmetry. Okay, so okay, now let's try to discuss the symmetry of the effective Hamiltonian. So for the simplicity, we consider the circuit with a Z2 parity symmetry generated, let's say, by the product of Z's. And if we force the circuit to have this symmetry, we know there are only some allowed terms allowed gates in this circuit. For example, like single qubit Z gate, 2 qubit Z gate, 2 qubit XX gate, blah blah blah. And the type of measurement is also restricted. Okay, when I say type of measurement, we respect the parity symmetry. I mean, each projector is actually commute with the symmetry generator, and the allowed measurement are like a Z measurement, ZZ measurement, or XX measurement. And okay, and this will be the circuit that I'm going to consider for this part. Okay, and the symmetry of HQ, as I said, symmetry of HQ actually comes from you perform the average over or perform average over certain unitary, but that symmetry is really encoded in the dynamics of double Hilbert space. So here let's see again this familiar diagram of the dynamics in double Hilbert space, and what are the symmetry of this dynamic of this dynamics. So first of all, regarding the symmetry of the circuit, there's going to be a S2 symmetry similar to the situation of Hall-random unitary, which correspond to the exchange of two, let's say two forward evolution, which is given by this light blue rectangles. And there's going to be, just at the tensor network diagram level, there's going to be a symmetry of exchanging these two. And what is
sorry, excuse me.
Yes.
That Z2 symmetry you wrote on the left side, is that just add by hand, or there's physical reason?
Oh yes. Okay. So I guess Xiaoliang, your question is, this Z2 symmetry is because we are considering two copies, and okay, to answer this question, so
okay, so I guess, yeah, I was just trying to clarify whether that's a symmetry of the physical system, or is that just a symmetry between the two copies?
Yeah, this is okay. For the Z2 symmetry is this swap symmetry about swapping two copies. This is not a physical symmetry, but we would expect this symmetry plays a role in the replica limit n goes to 1, because this symmetry exists for all the replicated quantities. And we also see in this entanglement phase transition that this the entanglement phase transition is really related to this the breaking of this swap symmetry of two copies.
But the parity symmetry is the physical symmetry. The
parity symmetry is the physical one, yes. Okay. So just look at the dynamics of two copies. Actually, we have two. We have the symmetry. So first, we have a swap symmetry of swapping two copies, and second, we have the parity symmetry. And this two symmetry actually will give rise to a D4 symmetry. And this is not the full symmetry of this dynamics. If you take a careful analysis of the of the symmetry, actually you will see the full symmetry is actually d4 by d4 for forward and both forward and backward copy, and there's another symmetry related to the hermeticity of the density matrix. But this is not really crucial. What is really important is there's an enlarged discrete symmetry in the doubled Hilbert space, and this determines the phases of information dynamics. Okay, so let's go back to our spin one model. Actually, not all the group element takes a non-trivial representation in the effective Hilbert space. If you look at the spin one models, describe this imaginary time evolution in the effective Hilbert space, it actually exhibits only a D4 symmetry. I have to say the complete understanding of which symmetry plays the non-trivial role and which is not, we haven't fully understand that. But starting from this D4 symmetry, we can already see, and there are going to be various different interesting phases. First of all, it can be symmetry breaking phase, either the swap and parity symmetry either breaking or preserving, and we can also expect a topological phase protected by D4. Although we haven't defined this topological phase in this model, actually I will show you an example of topological phase in another model later on. So now the question boils down to what is the meaning of those symmetry breaking phase, and what is the meaning of this novel phases in terms of going back to the quantum circuit. So maybe it's a good time to take a step back. Let's recall what is the meaning of swap symmetry breaking. So the swap symmetry breaking really correspond to this entanglement phase transition between the volume and the area law phase. And the volume law phase, as I showed in the background slide, is a broken symmetry phase, and the quantum information is being protected by the scrambling unitaries. On the other hand, we have this area law phase when symmetry is preserved, and this is the situation when information is revealed. So now the question is, so as I said, there's also possible to have this parity symmetry breaking phase transition in the model of consideration. So what the question is, what does it mean by parity symmetry breaking in terms of quantum information? Actually, we can guess the answer must correspond to some kind of information protection, and the naive guess is about the information about the conserved quantity. I'll show you in a second. Okay, so one way to understand this Z2 parity breaking phase transition is through the okay, let's consider this circuit with parity symmetry, and we try to measure the parity of a subsystem A in the final state. So okay, due to this measurement during the time evolution, we can define an ensemble of quantum trajectories, and what we can show is, so let's say there are two important ingredients in this circuit, which is a Z measurement or XX measurement. Actually, if the Z measurement is large, you will see that it's easy to understand that the final state is projected to an eigenstate of Z's, and the most trajectory will have a definite parity, which is going to be ±1. We call it parity revealing phase. There's another situation when XX measurement is large, and in this case, most trajectory will have an indefinite parity, which means the expectation value of the parity in the final state will be 0. And this is going to be a parity hiding phase. So one signature to probe this phase transition could be, so let's say we compute the parity for each trajectory and we square it and then average it over a different trajectory. And this is going to be a diagnostic of this phase transition. This gives a probe of the phase transition, but we still didn't resolve the question what is the how can we understand this parity phase transition from the dynamics of quantum information? Okay, I forgot to say, and this probe will go into a constant in the parity revealing phase and will be exponentially decaying in the parity hiding phase. So it turns out that we can also understand this parity phase transition from an information theoretical perspective. So instead of looking at the parity in the final state, now let's take a different perspective. We consider the Shannon entropy of measurement results. Let's say you have a fixed geometry of the circuit, and you perform measurement somewhere in the circuit, and you just take down the measurement result and repeat the measurement over and over, repeat the experiment over and over again. Then you accumulate a probability distribution for the measurement results. Then you can ask, what is the Shannon entropy of measurement results? So it's not okay. Now it's important we start from a parity definite state, and we compute the Shannon entropy for the measurement results. Okay, and then what we do, we perform a parity changing perturbation on the initial state, and we repeat the experiment again. We ask, what is the Shannon entropy of the measurement results? So if, let's say, if the parity information of the system is protected from being revealed by measurement, then this parity changing on the initial state will not be reflected in the measurement result. So it's natural to ask, to compute what is the change of Shannon entropy before and after you perturb the system by this parity changing operation. And it turns out we can use replica method to map to spin model, and it turns out this difference in the Shannon entropy reduces to, it can be related to the magnetization in the spin model, or in some sense the order parameter in the spin model. What is also important here is it's actually 1 minus order parameter, and this gives rise to the description of two phases. So first, in the parity revealing phase, we know the symmetry is preserved, and the order parameter in this spin model is actually small. And in this case, 1 minus order parameter will be large, and that means that the difference in Shannon entropy is large, and the measurement really revealed the information of parity. On the flip side, which is the parity hiding phase, when symmetry is broken and order parameter is large, in this case the difference in Shannon entropy is small, means the parity information is protected from the measurement. If you have a tuning parameter in your system, let's say the ratio of Z measurement versus XX measurement, you should be able to tune a phase transition across between these two phases, and the signature should be given relatively similar to what is given here on the right. And there's going to be a non-analyticity, which really sharply define the phase transition. Okay, any question?
It's almost 30 minutes, just a reminder.
Oh, okay, yeah. Okay, I'm going to finish very quickly in 5 minutes, yeah. So now I'm going to talk about the very last part, which is about the Gaussian fermion circuit. So in this Gaussian fermion, I'm considering the particular type of Gaussian fermion circuit, which is Gaussian fermion circuit. Each wave, which is a wave function in this dynamics, is always Gaussian, and this restricted type of unitary I can get is basically like a Gaussian fermion gate on site, or my fermion hopping gate, which is the gate generated by Majorana bilinears across different sites. I'm going to perform Gaussian measurements, basically measurement of the fermion occupation in this circuit, and which is either measure the fermion occupation on site or the fermion occupation on bound. Okay, and this circuit only conserves the Z2 parity symmetry. And there has been previous work studying this, showing that there actually cannot be any volume law phase for any non-vanishing measurement rate. And there's a recent work showing that there's going to be a phase transition from a logarithmic entanglement to area law entanglement. In this talk, I'm going to show there's actually a hidden U1 symmetry that governs this phase transition, and even larger SU2 symmetry in the absence of measurement. And this will actually explain all the results previously observed. Okay, so using this mapping to the ground state problem, actually we can show that this quantum circuit I'm showing in the previous slides, containing this 4 ingredient, will maps to a XXZ model with XXZ spin chain with single side anisotropy. There are a few ingredients like a hopping term, and the bond measurement and the site measurement. Let's first consider a situation when there's no measurement, and then this model reduces to a ferromagnetic Heisenberg model, and it's SU2 symmetric, and we will get a ferromagnetic ordered ground state, and this actually implies the volume law entanglement when there's no measurement. When there is a non-vanishing measurement, actually we can see this model still has a U1 symmetry, and it is not possible to spontaneously break this U1 symmetry in 1D. So which leads to, because no spontaneous symmetry breaking, which means there's an absence of volume law phase when there's no measurement. And actually the phase diagram of this model has been studied extensively, and there are actually 3 phases. There's going to be a critical U1 phase, and there's a trivial area law phase, there's a Haldane phase. And by tuning the measurement probability, you can actually tune a measurement-induced KT phase transition between these two. Okay, and let me briefly explain the origin of U1 and SU2 symmetry. This is really resides in the nature of 2 copies. So you consider 2 copies of density matrix. You basically have a Majorana model, let's say two forward evolution, and this combines can give you a U1 model. Basically, you construct a fermionic mode by a linear combination of Majorana fermions on different copies. And this actually, you can show this is a symmetry of the model. And in the case when there's no measurement, actually you have 4 copies of quadratic Majoranas, and which has 2 copies and their time reversal, which you can actually see it forms a SU2 spin 1/2 fermion chain, and there's apparently a SU2 symmetry there. This explains all the phase diagram we just observed. Actually, we have some problem figuring out the technical difficulty we haven't really sorted out to explain the behavior of observables in different phases, but we actually move on to do the numerics, and you can show, okay, here we consider special situation when there's no bond measurement, and the Hamiltonian is really this, and it's well known there's going to be a KT phase transition. And we actually see by increasing the measurement result, there is a phase transition from a power law decaying parity correlation to the constant parity correlation, which is basically a quasi-Lagrange ordered parity ordered phase to a parity symmetry preserving phase. And for the entanglement, there's going to be a phase transition from logarithmic to area law entanglement. Okay, this is some other work I'm also working on, like the measurement-induced phase transition in long-range circuit. If you are interested in this, we can talk offline. So here's the summary slides. Thank you so much.
Thanks, Yimu. Yeah, we can have maybe 1 or 2 questions. So I just want to confirm my understanding. So so the power law correlated spins in the U1 case corresponds to a log entropy.
Yes. So maybe we can go back a little bit. So we have an expression here. If you see the entanglement entropy is really minus log of the matrix element here. Actually, you can show this matrix element maybe exhibits something similar, has a similar behavior of correlation function, which is a power law correlation. And if you take a log, that will give you a log entanglement entropy.
And physically, where is the U1 symmetry from?
Physically, okay, this U1 symmetry is only exists when you consider 2 copies. And okay,
yeah,
there is physically. Yes.
I mean, yeah, you have 2 copies, but why do you have a continuous symmetry U1?
Sorry, why do you have?
Why do you have a continuous U1?
Okay. Because in each copy, I have a Majorana model, which is like a hopping of Majoranas on a 1-dimensional chain. And if you have 2 copies, you have two chain of Majorana. If you just combine these 2, it is actually a fermion hopping model on a 1-dimensional chain, right?
Okay. Any other questions? Okay, if not, let's thank Yimu and thank all the speakers of the first session.